In the name of God, the compassionate, the merciful. I am Abdullah Dusti Aref. This presentation is related to part of my research effort in which some challenging issues concerned with ambient noise, our underwater acoustic channel, are addressed. The title of this talk is Modification of Venn Formula, or MWF algorithm, which addresses a simple method for modeling the power spectral density of ambient noise in the seawater based on the experimental measurements of any. At the first, to show the necessity of more investigation about the underwater world, I would like to emphasize to this fact that nearly 71% of the Earth's surface is covered with water, and 97.5% of it being seawater. This vast underwater world is extremely rich in minerals and oil resources, which today, because of the technological advances, we are able to exploit them. In recent years, design and implementation of efficient underwater acoustic systems have been receiving an increasing attention in both military and civilian applications. One of the most challenging features of underwater acoustic channel is ambient noise. Unlike radio frequency terrestrial channels, in which noise is statistically modeled with a wide Gaussian stochastic process, the power spectral density of ambient noise in underwater acoustic channel is not wide. As a result, working over underwater acoustic channel is much more complicated than terrestrial radio frequency channel. In order to efficiently design and analyze sonar and underwater acoustic communication systems, utilizing suitable model for ambient noise leads to more promising performance. In this context, this presentation addresses a simple method for modeling of the power spectral density of ambient noise in the seawater based on the experimental measurements of any interest region. There are many sources for ambient noise, such as rainfall, sound waves of shipping, seismic events, thermal agitation, and so on. In literature, most of them have a continuous spectrum and are characterized by normal stochastic processes. During World War II, because of the availability of calibrated equipment and the necessity to understand ambient noise levels in coastal areas, a study of ambient noise was an active area of research. This wartime research was first summarized by Knudsen and later by Urich and Prigg in 1954. By the early of 1960s, the research in this area waned. Eventually, in 1962, Vance introduced a seminal work and developed a model for PSD of ambient noise under the sea. Accordingly, his work initiated a renaissance of ambient noise as one of the most appealing areas of oceanic acoustic research. In recent decades, researchers have done some studies in this area by applying Vance's model and have confirmed it. According to the widely used Vance model, there are four main sources of ambient noise, each of which becomes dominant in a special frequency range. The power spectral density of ambient noise in dB reference to 1 micropascal per hertz is given by equation 1, in which the four terms NLTU, NLSS, NLTR, and NLTH stand for noise level as a direct consequence of turbulences, sea state, shipping traffic, and thermal load, respectively. They are functions of frequency in kilohertz, wind speed in meter per second, and the shipping activity factor SA, whose value falls between 0 and 1 for low and high activities, respectively. In some literature, for the sake of simplicity in modeling of the ambient noise, unlike what is seen in reality and what is found by Vance's model, namely colored Gaussian model, researchers have used white Gaussian noise model and the related results which have been demonstrated in terrestrial radio frequency channels. Furthermore, in some literature, the power spectral density of ambient noise approximately decays at 18 dB per decade for the frequency range of 100 Hz to 1 MHz. According to the Vance model, as illustrated in the right figure, applying such assumptions is not reasonable. First, all over the frequency range, the diagram slope is not negative. For example, in frequencies more than 100 kHz, the diagram slope is positive. Moreover, in the frequency range of 10 to 100 kHz, although the diagram slope stays fixed with the value of minus 18 dB per decade, the integral of the PSD, giving the noise power, significantly alters in consequence of the variations of wind speed. For instance, by changing wind speed from 5 meters per second to 15 meters per second, the noise power increases 25 dB. In this section, based on the experimental data which can be acquired from any interest region, a general algorithm is addressed for modification of Ven's formula in the frequency range of 100 Hz to 100 kHz. According to the Ven's model, the PSD of ambient noise in dB reference to 1 micropascal per Hertz is given by equation 1. As depicted in this figure, Ven's model confirms this physical fact that in the frequency range of 100 Hz to 100 kHz, C-state noise is the major contributing noise. As a result, the total ambient noise becomes equal to the PSD of the C-state noise. Therefore, due to the extra low impact of other three terms in equation 1, in the frequency range of 100 Hz to 100 kHz, we can properly simplify equation 1 to equation 2, in which the parameter gamma describes the profile of wind speed in meter per second. Equation 2 has been written in dB and can be numerically written as equation 3. Since in the frequency range of 100 Hz to 100 kHz, the frequency parameter f is much bigger than 0.4 as depicted in the figure, equation 3 can be properly approximated as equation 4. Through this approximation, the PSD of ambient noise becomes statistically similar to the PSD of a fractal stochastic process with a spectral parameter 2. It is worthwhile to point out that such processes are not wide-sense stationary or WSS. However, for short observation of time, in the frequency range of 100 Hz to 100 kHz, experimental measurements have proved that the ambient noise appears stationary in most of the Cs. In what follows, I aim to approximate the non-stationary fractal stochastic process by a stationary process. Since the integral of the PSD gives the power of noise and also ambient noise power is finite, we add the parameter lambda to the denominator in equation 4. Therefore, we obtain equation 5. As a result, in equation 5, noise level does not diverge at low frequencies and consequently the integral of the PSD becomes finite. Let me define the parameter P0 as given in equation 6 and define the parameter f0 in kHz as half power bandwidth given in equation 7. As a result, the parameter lambda would be equal to the square of f0 in equation 8. In other words, the parameter f0 is the lowest frequency below which the shape of the PSD varies in a manner whose integral becomes finite. Therefore, we obtain equation 9. Accordingly, the ambient noise power is obtained by the integral of equation 10. Finally, the modified form of Ven's formula as a function of frequency and wind speed profile is obtained as equation 11. In this section, the mathematical proof of ergodicity is presented. According to Wiener-Hintgen theorem, by taking the inverse Fourier transform of equation 11, we can readily obtain the corresponding autocorrelation function as equation 12. Since in proposed model noise mean is 0 and the autocorrelation function is merely dependent on the parameter tau in equation 12, the ambient noise in the frequency range of 100 Hz to 100 kHz can be approximately assumed as a WS's stochastic process. Meanwhile, due to the fact that each normal WS's process is strict sense stationary, the ambient noise can be approximately assumed as an SSS process. Since ambient noise is a normal, zero mean, and SSS process, its autocovariance function, namely Cn2, is equal to its autocorrelation function given in equation 12. According to Slotsk's theorem, a WSS process is mean-ergodic if and only if this integral tends to zero. Moreover, a WSS normal process is covariance-ergodic if and only if this integral tends to zero when the parameter 2 tends to infinity. By applying the theorem to the autocorrelation function in equation 12, we obtain equation 14. Therefore, ambient noise is covariance-ergodic. By using Schwartz inequality, equation 15 is easily concluded. It means that if a normal process be covariance-ergodic, it would be mean-ergodic as well. Therefore, ambient noise is mean-ergodic. Since covariance function tends to zero, as the parameter 2 tends to infinity, the random variables of the noise process at times t and t plus 2 are uncorrelated for large value of 2. Moreover, they are joint to normal. As a result, they are independent for large value of 2. According to Slotsk's theorem, a process is distribution-ergodic if and only if equation 16 is satisfied. In equation 16, the parameter f denotes the cumulative distribution function. Accordingly, a sufficient condition is obtained from the independency of random variables of the noise process at times t and t plus 2 for large value of 2. Therefore, ambient noise is distribution-ergodic as well. Furthermore, a straightforward proof can be employed by the spectral interpretation of ergodicity that a stochastic process is mean-ergodic if and only if its PSD has no impulses at the origin. Moreover, it is covariance-ergodic if and only if its PSD has no impulses anywhere. According to the mentioned proof, ambient noise in the frequency range of 100 Hz to 100 kHz can be generally approximated with a strict sense stationary colored normal stochastic process, which is ergodic not only in mean and covariance but also in distribution. Since in both proposed model and measured data, there is no impulses in the PSD of ambient noise, the mean of ambient noise is zero. As a result, equation 10 gives the ambient noise variance, which is merely dependent on the profile of wind speed. Based on Wend's formula, the parameter gamma in equation 10 is merely dependent on wind speed. Therefore, to obtain a suitable formula, the parameter gamma should be tuned based on the experimental data. In experimental tests, it is possible to measure the ambient noise power for different values of wind speed. Such experimental data enable us to obtain a suitable profile for ambient noise variance in terms of wind speed. According to the above derivations, MWF algorithm is proposed as a method for modification of Wend's formula for the frequency range of 100 Hz to 100 kHz. By utilizing such a simple method, one will be able to efficiently model both the PSD and the corresponding autocorrelation function of ambient noise in any interest underwater acoustic channel. In this section, the performance of proposed algorithm is evaluated based on the experimental data. A Strait of Hormuz, owing to its abundant oil and gas resources, is militarily, economically, and politically a strategic region, which is known as a shallow water channel worldwide. During the period from December 2014 to June 2015, extensive sea experiments were conducted in the Strait of Hormuz by Iranian experts. The location of experiment site along with its borders are illustrated in this figure. The main goal of the experiments was first to find the source regions of dense water formation that derive the outflows, and second to measure some channel characteristics such as salinity distribution, temperature salinity profile, absorption loss, and ambient noise. Both passive and active sonar subsystems were employed via a submarine to acquire the appropriate experimental data. The active sonar was bow-mounted, and the passive one was hull-mounted. As illustrated, the water depth around the experiment site was variable from 50 to 105 meters. The distance between the borders B1 and B3 is 43.03 kilometers, and the distance between B2 and B4 is 32.63 kilometers. Experiments were carried out at different days from December to June, as well as at different times of a day under different scenarios. It should be noted that the average values of experiments are used in this work. To evaluate the performance of proposed algorithm by experimental measurements, the average value of 3,000 samples is utilized at each depth for computing the parameters such as temperature, salinity, and absorption coefficient. It is worthwhile to point out that due to large seasonal variations in the temperature and salinity, changes in the seasonal pattern of sound speed was evident from December to June. Unlike what was observed in both autumn and spring, namely considerable decrease of sound speed from surface to bottom, vertical sound speed profile increased from surface to bottom and had negligible changes during the winter. In this study, we utilized the approximate sound speed profile presented in reference 2 for the Strait of Hormuz and the related calculations. To measure the absorption loss at an arbitrary depth, different carrier frequencies were utilized, while the related temperature and salinity of water were simultaneously recorded via individual sensors. Each experiment was recorded during 5 hours. During an hour, 600 samples were acquired. In other words, the channel was captured 10 times a minute. As a result, the number of samples for each measurement point was 3,000. The ambient noise was measured by a line area of hydrophones, which was vertically ranged via a buoy located at point NB in the following figure. It is noteworthy that during the field tests, the sea conditions, especially the wind speed, at the sea surface were recorded. In what follows, the performance of proposed algorithm is evaluated by using the mentioned experimental data in the Strait of Hormuz. In this figure, comparing experimental data with the outputs of Venn formula confirms that there is a considerable difference between our findings in the Strait of Hormuz and the outputs of Venn's formula under the same conditions. Thus, utilizing Venn's formula in that region and planning based on it do not lead to promising performance. Therefore, based on MWF algorithm and by utilizing field measurements, the parameter gamma is approximated as a function of wind speed in this figure. As obviously seen, the approximate curve is closely matched with the measurements. Therefore, the continuous PSD of complex valued equivalent baseband ambient noise for the frequency range of 100 Hz to 100 kHz in the experiment site can be approximated in terms of wind speed by equation 17. According to our findings in the Strait of Hormuz, measured PSD had no impulses anywhere. This could be likely due to the absence of a snapping shrimp in that region. Therefore, the ambient noise in the Strait of Hormuz can be approximated by a colored normal streak since it's a stationary stochastic process, which is ergodic not only in mean and covariance but also in distribution. To evaluate the performance of proposed formula, the outputs of original Venn's formula are compared with both the experimental data and proposed formula under the same condition and 2 different scenarios. In the left figure, it is clearly seen that for wind speed of 15 meters per second, There is nearly 16 decibel difference between the outputs of Venn formula and our findings. However, the results of proposed formula confirm a close match with experimental data. Similarly, in another scenario in which wind speed is decreased to 10 meters per second, there is a still significant difference between measured data and the outputs of Venn's formula. Whereas proposed formula is matched with our findings with an excellent accuracy. See the right figure in this case. Therefore, equation 18 gives a suitable approximation of the noise PST for the frequency range of 100 Hz to 100 kHz in the Strait of Hormuz. The main contributions described in this talk can be concluded as follows. Number 1. The main goal of this study was addressing a simple algorithm for modification of Venn's formula in the frequency range of 100 Hz to 100 kHz based on the experimental measurements of any interest region. Number 2. It was mathematically proved that the ambient noise in the sea environment in the frequency range of 100 Hz to 100 kHz can be generally approximated with a strict sense stationary colored normal stochastic process, which is ergodic not only in mean and covariance but also in distribution. Number 3. The performance of proposed algorithm was evaluated by the experimental data of the Strait of Hormuz. Results of this research could be good guidance to study considerations for the deployment and operation of physical layer of underwater acoustic sensor networks. At the end, this research is dedicated to my teachers, the 175 immortal divers who were martyred in the imposed war and holy defense in the Islamic Republic of Iran in 1986.